So imagine you're sitting at your computer, right? And you ask your AI to do something, relatively quick.
Like a basic query.
Yeah, exactly. Maybe write a polite email to a client or summarize this really dense, like 10-page PDF, and it spits out a perfect result in, what, 3 seconds?
It genuinely feels like magic sometimes.
It totally does. But, I mean, it's magic for those compact, well-defined tasks.
Right, because the boundaries of what you are asking it to do are very clear there. And the tool it needs to use is really just its own text generation capability.
Exactly. But then, you get a little ambitious. You ask it to do something with, like, a few moving parts.
Oh yeah, the real world stuff.
Right. Something like, plan my upcoming business trip to London, find a flight that gets in before noon, book a hotel near the conference center, make sure the hotel has a gym, and, I don't know, schedule a dinner reservation with my clients for Tuesday night.
And that is usually where the illusion of magic abruptly shatters.
It totally falls apart. I mean, it might hallucinate a flight that doesn't even actually exist, or it forgets to check if the hotel has a gym.
Or it just gives up entirely.
Yeah. My personal favorite is when it just gives you a list of links and says, here you go, you can book these yourself.
Which completely defeats the purpose.
Exactly. It just stumbles the second it has to step out of that cozy chat box and actually execute something complex in the real world. But today, our mission on this deep dive is to explore how that exact limitation is finally being solved.
And it's about time.
It really is. So we are diving into a brand new foundational paper called ToolVerse. And it is honestly exactly what it sounds like. It's an absolute universe of tools designed to finally teach AI how to navigate these massive, complex, real-world environments.
It is such a phenomenal piece of research.
Yeah.
Because it directly attacks this gap between an AI that can only talk and an AI that can actually do things.
Right.
The researchers are essentially asking, how do we teach a model to take actions over a long timeline using dozens of different software applications without, well, losing its mind halfway through?
Okay, so let's unpack this. Because understand why ToolVerse is such a massive breakthrough for you, the listener, we first have to understand exactly why these incredibly smart AI agents get so hopelessly lost in the woods when we ask them to, string together multiple actions.
Yeah, and to do that, we really need to look at how they are currently trained. Today's large language model agents, or LLM agents, they're actually quite good at what we call compact tool scenarios.
Like using just one thing.
Exactly. If you give them a single tool, like a Python code interpreter or, say, a web search engine, they can use it effectively to get an answer.
Right, because it's just a one-and-done action. You ask a question, it searches, it gives you the answer. Mission accomplished.
But the real world rarely works that way. Real-world tasks are what researchers call long horizon.
Meaning they take a while.
Yeah, they require multi-turn, multi-step actions. You have to use one tool to gather information, which you then feed into a second tool, which might dictate the specific parameters of how you use a third tool.
Oh, wow, so it cascades.
It does. And when current models try to learn this behavior during their reinforcement learning phase, they crash into this huge wall called the credit assignment problem.
Okay, wait. Now, I've heard of credit assignment in finance, but what does that mean for an AI trying to book a flight and a hotel?
So think of it as a grading issue. In current multi-turn training, the feedback an AI receives is usually this thing called a sparse terminal reward.
Sparse terminal reward.
Which basically means the AI only gets graded at the very, very end of a long sequence of API calls and data retrievals. It gets like a 1 for success or a 0 for failure.
Just at the end. Okay, I think I have a good way to visualize this. Imagine like a chef cooking a massive, complex 10-course meal for a VIP customer.
Oh, I like this.
Right. So the chef spends hours chopping, sautéing, baking, plating everything perfectly. But the only feedback the chef receives is at the very end of the night. And that feedback is simply whether the customer left a tip or not.
Exactly. A binary signal at the end of a very long horizon.
Right. So if the tip is 0, the chef is just standing there in the kitchen completely lost. Was the soup too salty? Did they, overcook the steak? Did they use the wrong fork for the salad course?
The chef has absolutely no idea which of the hundreds of actions ruined the meal.
Yeah, that is wild.
But that is the perfect analogy. And in the context of agentic reinforcement learning, that lack of granular feedback is completely paralyzing for the model.
Because it doesn't know what to fix.
Right. It leads to incredibly high variance in the training data. The AI essentially gets confused. It might have executed, say, the first 8 steps of a travel booking perfectly, but it failed on step 9 because it formatted a date wrong.
Oh, man. So because it only gets a 0 at the end of the entire process?
It might discard the completely correct logic it used for the first 8 steps.
It's literally throwing the baby out with the bathwater because it doesn't know where it made the mistake.
Which leads to poor sample efficiency and severe training instability.
Mm.
The model just can't figure out which specific action caused the failure, so it really struggles to improve.
Wow. Okay, so if they can't learn because the feedback is too sparse and they can't practice because real-world APIs like actual banking or travel websites are, too risky and messy, how do we fix it?
Well, you have to build a new world for them.
Exactly. The researchers realized that since AI agents can't learn without a proper place to practice, they had to build them a training ground, but not just a simple, text sandbox.
No, they needed a training ground as messy, complex, and interconnected as the real world.
Which presents an enormous logistical hurdle, I would imagine. You obviously cannot unleash an untrained, experimenting AI onto the live internet to, practice booking flights and transferring money.
Definitely not.
Wait, I actually have to ask. When companies train these agentic models, are the AIs ever actually out there swiping real corporate credit cards or making actual reservations during their training phase?
Never. The liability would be astronomical.
Yeah, I figured.
Instead, researchers usually rely on static data sets. But the ToolVerse team took a completely different approach. They created an automated pipeline to scale up what they call executable environments.
Executable environments.
Yeah. They went out and gathered raw tool definitions from various open source and proprietary repositories. We're talking about JSON files that describe the parameters of how real-world tools actually work.
Okay, but a JSON file is just a text document, right? It describes data, but it doesn't really do anything. How is an AI clicking a button or making a query on a static text file?
That is where the engineering gets really clever. They used a technology called the Model Context Protocol, or the MCP library, as a bridge.
Okay, the MCP library.
Right. It acts as a translation layer. The researchers built an automated process that takes those static JSON descriptions and uses MCP to wrap them into fully executable Python scripts.
Oh, wow. So the AI isn't just reading text.
Exactly. It's interacting with a piece of code that behaves exactly like the real API would.
And to solve the credit card problem, like the fake money.
They built a mock database using Python dictionaries to sit right behind those Python scripts. This perfectly mimics the stateful nature of the real world.
Okay, wait. Stateful, let me make sure I understand that. Does that mean, if the AI books a ticket in the simulation, that ticket is actually gone from the inventory? The state of the simulated world has changed?
You've got it perfectly. If the agent queries the mock database for a flight, it gets a realistic response about availability.
Nice.
And if it issues a command to book that fake ticket, the fake inventory actually updates. If it immediately tries to book that exact same ticket again, the mock database will throw an error and say, sorry, the ticket is sold out.
That is so cool.
It really is. This allows the AI to experience the permanent consequences of its actions in a closed loop without any real-world risk.
And the scale of the simulated world is just wild. I mean, they didn't just build 10 or 20 of these environments. They rigorously tested thousands of them, running syntax checks, unit tests, and they just threw out anything that didn't work perfectly.
They had to be ruthless with the quality control.
Yeah. And what they were left with was 422 real-world environments containing 4,438 distinct tools.
What's fascinating here is how broad those domains are. We're talking data and information, personal assistance, finance and commerce, travel, health and fitness.
It covers basically everything you do online.
Exactly. It is a massive, highly diverse, fully interactive simulation. They essentially built a localized matrix for the AI to train inside.
Okay, so they built the matrix, but, you can't just drop someone into the matrix and expect them to suddenly know Kung Fu.
Right, you need training.
Yeah, if you put an untrained AI in a room with 4,000 tools, I imagine it's just going to start pressing buttons randomly. How did they force it to learn the actual order of operations?
That brings us to their curriculum design. They developed a framework called graph-based long horizon task synthesis.
Graph-based.
Okay, yeah. Now that we have 4,000 executable tools, we have to teach the AI the logical order in which to use them.
I mean, I would assume they just feed the AI a giant instruction manual for all 4,000 tools and tell it to figure out the connections. Figure it out yourself.
That would be the intuitive approach, for sure. But it actually overwhelms the model with way too much context. Instead, the researchers created what they call a tool dependency graph, or TDG.
A dependency graph.
Right.
Yeah.
It mathematically maps out which tools absolutely must come before others. It defines the parameter dependencies, meaning the output of tool A is literally required as the input for tool B.
Oh, I get it. Like if I'm planning a trip, I physically cannot use the book flight tool until I have successfully used the select destination tool.
Yeah.
There is a rigidly required sequence.
Exactly. And to actually generate the training tasks from this massive map of dependencies, they used an algorithm called dynamic unlocking sampling, or DUS.
And I love how they implemented this because it's almost exactly like a video game skill tree.
It really is.
Right. Tools that have dependencies are literally locked in the environment. The AI cannot even access them or see them until the prerequisite tools have been successfully used.
But locking the downstream tools, this topological constraint prevents what we call causal errors. It guarantees the AI is learning actual logic, not just getting lucky by guessing the final step.
Wow.
It forces the model to progress through a very coherent cognitive flow.
And all of this careful mapping, this whole curriculum, led to the creation of the GST dataset graph unlocking sampling tasks. It's a dataset of nearly 3,000 highly complex, logically sound training items, and they rigorously verified every single one of them using the strategy called Pass at 8.
Yeah, Pass at 8 is a fascinating quality control measure.
Yeah, let's break that down because my understanding is they basically bring in a highly capable teacher AI, like a massive state-of-the-art model, and give it the task. And they give the teacher agent 8 separate attempts to solve it.
Right.
If the smartest teacher model fails all 8 times, the researchers basically assume the task itself is either broken, logically impossible, or missing a tool, and they just throw it out of the beta set entirely.
It's brilliant because it ensures that every single scenario in the GOST dataset is actually solvable by an AI. It prevents the trainee models from wasting time on broken logic.
Right, which would just confuse them more.
Exactly. And to really see how this works in action, let's put you in the shoes of the AI. Let's look at the specific example they provided in the paper, which involves booking a trip to see Taylor Swift.
Oh, the Taylor Swift Tokyo scenario. This perfectly illustrates what this new breed of AI is actually doing. So the prompt from the user is simple. They type, "Help me book a trip to see the Taylor Swift concert in Tokyo next month."
Now think about what a standard older AI would do with that prompt. It might just spit out a link to Ticketmaster and a link to Expedia and tell you to have a nice trip.
Which is so frustrating.
Right. But the ToolVerse trained agent approaches this completely differently. First, it uses the search event tool. It inputs the query Taylor Swift and the city Tokyo.
Okay.
And the mock database we talked about earlier responds, telling the agent the concert is at the Tokyo Dome on February 14th.
So now it actually has the venue and the date.
Yes. So it moves to the next logical step. It wants to use the book hotel tool. But because of that tool dependency graph, the agent realizes that the book hotel tool requires a parameter it doesn't have yet, a maximum price. It needs a budget.
Okay, and this is the brilliant part to me. Because it doesn't just guess a budget or hallucinate a random number.
Not at all.
It actually pauses its tool execution and reaches back out to the user. It says, "I found the concert at Tokyo Dome on Feb 14th. I can book a hotel nearby. What's your nightly budget?" And then the user replies, "Keep it under $200.
And only then, armed with the venue, the date, and the newly acquired budget constraint, does the agent execute the final tool, successfully booking the hotel and confirming it.
It's essentially forcing the AI to develop patience. It's teaching it to use a cognitive checklist, much like how we humans pack for a trip, you know? You don't just throw random items in a suitcase. You check the weather, you plan your activities, and then you pack. It's logical patience.
And that logical patience needs to be graded correctly, which brings us to the most critical innovation in this entire paper, in my opinion.
Right.
We have the environment, we have the curriculum, but how do we solve that 10-course meal problem we talked about at the beginning?
The tipping problem. Right, if the AI gets to the end of that Taylor Swift scenario and fails, how does it know if it messed up the concert search, or the budget question, or the hotel booking?
To solve this, the researchers threw out the old grading system entirely and introduced TARA. That stands for Turn-Aware Relative Advantage.
Turn-Aware Relative Advantage. Okay, let's explain why this is so much better than the old way.
Well, the old standard for grading these models is a trajectory level system called GRPO, to put it simply. Trajectory level means the AI only gets a single grade for its entire journey, its entire trajectory from start to finish.
Got it.
If it took 20 steps, it gets one score for all 20 steps combined. It is the single tip at the end of the 10-course meal.
So, if GRPO is the single tip at the end of the night, Tara feels like having a master sous chef standing next to you in the kitchen, tasting the soup, checking the steak temperature, and grading every single dish as it leaves the kitchen.
That captures it perfectly. Terra grades the AI turn by turn, and it splits that turn-by-turn grade into two distinct parts: local advantage and gated future advantage.
Okay, let's break those down. Local advantage is basically asking, did the agent get this specific immediate step right? Like when it searched for the Taylor Swift concert, did it input Tokyo correctly compared to other attempts it made?
Exactly. It's assessing the immediate correctness of the action in isolation. But that's not enough, because a correct action might still lead you down a dead end if it's not aligned with the long-term goal.
Right, like you did the math right, but you're solving the wrong equation.
Exactly. That's where gated future advantage comes in. It asks, did this specific action ultimately lead to future success?
But there's a massive catch here, and it's honestly my favorite part of the math in this paper. It's called the consistency gate. It's vital.
Now, if I'm understanding this right, does the consistency gate just mean it checks if the final hotel booking actually went through, regardless of how it got there? Like, as long as the end result is good, you get the points.
Actually, it's the exact opposite, and that distinction is super crucial. If you reward an AI just because the end result was good, you run the massive risk of creating a superstitious AI.
Superstitious.
Yeah, in machine learning, we call these distractors. Imagine the AI makes a completely wrong move on step 3, like it makes a lucky guess, or it hallucinates a parameter. But the environment happens to be tolerant enough that the AI still manages to stumble across the finish line on step 10.
Oh, I get it. Like getting the math problem completely wrong in your scratch pad, but accidentally writing down the correct multiple choice letter anyway?
Exactly that. Without the consistency gate, the AI's underlying reinforcement learning algorithm looks at the final success and says, wow, whatever you did back on step 3 must have been brilliant.
Right. It reinforces incorrect, superstitious behaviors. But Tara's consistency gate acts as a strict mathematical filter. The agent only gets credit for future success if the current step it just took was logically valid.
Ah.
If step 3 was invalid, the gate closes. The future reward for that specific action drops to 0.
So if you drop the steak on the floor during prep, you don't get any credit for how nicely it was plated later on.
Precisely. In fact, the algorithm mathematically forces the advantage for those distractors to be strictly negative. It completely roots out the lucky guesses and only rewards genuine, coherent logic.
That is deeply satisfying. It's really just weeding out the fakers. So we have this massive 4,000 tool simulated matrix. We have the graph-based curriculum teaching patience, and we have Tara acting as the strict sous chef, giving these incredibly precise turn-by-turn grades.
It's quite the setup.
It is. The architecture sounds flawless in theory, but does it actually translate to a smarter AI for the end user? Like, does this actually work?
The results are, frankly, undeniable. The researchers evaluated ToolVerse across 3 major, highly rigorous multi-turn benchmarks.
And let's talk about those benchmarks, because they aren't just simple, like, Q&A tests, right?
No, they test complex execution.
Yeah.
So BFCLV3 evaluates how accurately a model can call functions without making syntax errors.
Okay.
Ta2Bench challenges models to handle multi-turn interactions with really messy, realistic APIs.
Right.
An ECBench agent is perhaps the most difficult. It tests how well an agent can operate software interfaces and string together multiple commands to achieve a high-level user goal.
And the performance gains across all 3 were just universal. The numbers that really jumped out at me were for the Qwen38B model, which is a thinking model designed for reasoning.
A very strong model.
Yeah. On the ACDbench agent benchmark, its baseline score was 46.51, but when it was trained with the full ToolVerse framework and Tara, that score skyrocketed to 61.66. That is a massive leap for a model of that size.
And what's equally impressive is that it didn't just work on the thinking models. They also tested it on standard, non-thinking instruction models, like Qwen 2.5-14b. And they saw massive double-digit jumps there as well.
They also ran an ablation study, right, where they selectively turned off certain parts of the framework to see how much they mattered.
Yes, and this is where they proved why building the matrix was so important. They showed that scaling the environments directly improved the AI's ability to handle brand new, totally unseen tasks.
Oh, wow.
They trained one version of the model on 100 environments and another on the full 422. and the model trained on the larger data set showed a massive spike in its generalization abilities.
Meaning it could adapt better.
Exactly. It mathematically proved that exposure to a wide diversity of tools is critical for building robust reasoning. The more varied the tools it trains on, the better it handles completely unfamiliar tools in the real world.
So what does this all mean? Like for you, the person listening right now, this means we are rapidly moving away from an AI that just gives you a static recipe for dinner.
Right, the old way.
Yeah. We are moving toward an AI that can check your smart fridge, cross-reference it with the recipe, order the missing ingredients from an online grocery API, coordinate the delivery time with your calendar, and thanks to that consistency gate guarantee that it doesn't accidentally charge your credit card for 100 pounds of flour just because of a hallucinated parameter.
If we connect this to the bigger picture, the true power of ToolVerse is that it provides a completely model-agnostic training paradigm.
Which is huge.
It is. It fundamentally upgrades how any agent interacts with real-world APIs. It doesn't matter whose proprietary or open-source model you are using, this framework offers a universal blueprint for turning passive chatbots into autonomous, reliable operators.
It is shifting the entire landscape from text generation to reliable action execution. So to wrap up our journey today, we started with models that get lost in the woods because they only get a single tip at the end of the night.
The 10-course meal problem.
Exactly. Then we explored the simulated mock databases of the ToolVerse matrix built with the MCP translation layer. We saw how the GUST dataset uses graph logic and skill trees to teach AI patience. And we learned how Tara acts as the ultimate strict sous chef, weeding out lucky guesses to build true causal reasoning.
It's a remarkably comprehensive solution to one of the most stubborn bottlenecks in artificial intelligence.
It really is. But before we go, I want to leave you with a final thought to mull over. ToolVerse essentially built an incredible matrix for AI to master thousands of human-made tools. But as these agents get better and better at stringing together 10, 20, or even 50 tools to solve incredibly complex goals over long horizons, what happens when they encounter a problem where the right tool doesn't exist?
That's definitely the natural next frontier. I mean, if an agent truly understands the logic of 4,000 tools, what stops it from identifying a missing link?
Exactly. Will the next step in agentic reinforcement learning be an AI that recognizes a gap, pauses, writes its own code to build a brand new tool from scratch, seamlessly integrates it into its own dependency graph, and solves problems we haven't even learned how to articulate yet?
It's entirely possible.
Because if it can master 4,000 tools, creating tool number 4001 might just be the next logical step. The chef isn't just waiting for the tip anymore. They might be getting ready to redesign the whole kitchen, something to mull over until next time.